Imagine standing in the middle of the Amazon rainforest. You hear birds calling, insects humming, leaves dripping with moisture. Above you, towering trees. Around you, life everywhere. But what if I told you that beneath your feet, far deeper than any tree root could ever reach, another river may be flowing? Not beside the Amazon, not branching from it, but below it. Thousands of meters underground. Now pause for a second and really let that sink in. A river under a river. No sunlight, no riverbanks, no waves, no sound, no movement you could ever see. So how could something like that even exist? That's where this story gets fascinating. Deep below the rainforest floor, scientists believe there is a vast, hidden system of water slowly moving through layers of porous rock. It doesn't rush like the Amazon above. There are no crashing currents, no swirling eddies. Instead, this underground river moves at an almost unimaginable pace so slowly that a single drop of water could take hundreds of years to travel from one end to the other, centuries. Think about that. Empires rise and fall, languages disappear, entire civilizations change, and that one drop of water is still quietly moving through stone. This mysterious system is known as the Hamza River. And here's the most surprising part: it wasn't discovered by adventurers hacking through the jungle, not by satellites scanning the Earth from space, not even by scientists who were looking for a river at all. It was found hidden inside something far less romantic: old oil drilling data. Decades ago, engineers drilling deep into the earth beneath the Amazon collected temperature and pressure readings from hundreds of wells. At the time, the data was simply archives stored, forgotten, and moved on from. No one thought it had anything to do with rivers or water systems. Years later, scientists took another look, and what they noticed made them stop. Across an enormous area, the data showed something strange: consistent patterns of heat and movement deep underground. Patterns that didn't match solid rock. Patterns that looked eerily like flowing water. But how could water flow without channels? Without gravity pulling it downhill the way rivers normally move? That question alone forced scientists to rethink everything they thought they knew about how water behaves beneath the Earth's surface. Unlike surface rivers, the Hamza River doesn't carve its path. Instead, it seeps through microscopic spaces between grains of rock. The water is guided not by steep slopes, but by pressure differences deep within the Earth. It's slow, silent, and completely invisible to the world above, and yet its influence might be enormous. Some scientists believe this hidden river could play a role in how the Amazon rainforest survives long periods of drought. When rainfall decreases, could underground water systems like this be quietly feeding moisture back into the ecosystem? Could this slow-moving river be acting like a natural reservoir, storing water over centuries and releasing it when the surface needs it most? And then there's the bigger question: if a massive underground river can exist beneath the Amazon, how many others might exist elsewhere on the planet? How many hidden systems are quietly shaping Earth's climate, ecosystems, and water cycles completely out of sight and completely unknown? The Hamza River challenges something deeply human about the way we see the world. We trust what we can observe, what we can map, what we can photograph. But this river reminds us that some of the most powerful forces on Earth don't announce themselves at all. They work slowly, silently, patiently, and sometimes they stay hidden for centuries until someone knows how to look. This isn't just a story about a river. It's a story about everything we don't see and how those unseen systems may be shaping the future of our planet right now. And this is only the beginning. Most great discoveries come with dramatic images in our minds. Explorers hacking through jungles, scientists standing beside massive machines, satellites scanning the Earth from space. But the story of the Hamza River begins in a much quieter way. No jungle expeditions, no breaking news headlines, just a laboratory, old data, and a scientist who knew how to listen to numbers. It was 2011, inside a conference hall in Rio de Janeiro during the 12th International Congress of the Brazilian Geophysical Society. Two researchers stepped forward to present a short abstract. Its title didn't sound revolutionary at first glance: Indications of an Underground River Beneath the Amazon River. Inferences from Results of Geothermal Studies. Not exactly something you'd expect to rewrite textbooks. And yet, that presentation would quietly challenge how scientists understand water beneath the Earth's surface. The lead author was Valia Manathal Hamza, a geothermal scientist originally from Kerala, India. He had moved to Brazil decades earlier, back in 1974, and spent nearly 40 years studying how heat moves through the Earth. Alongside him was Elizabeth Tavares Pimentel, a researcher who helped analyze one of the most unlikely sources of discovery you could imagine. Because the data they used wasn't new, it wasn't collected for this purpose, and no one had been looking for a river when it was recorded. The dataset came from 241 deep boreholes drilled across the Amazon basin by Petrobras, Brazil's state-owned oil company. These wells were drilled in the 1970s and 1980s. During intense petroleum exploration, their goal was oil, plain and simple. But as part of routine drilling, engineers recorded thermal profiles, temperature measurements taken at various depths underground. Once the drilling ended, those temperature logs were archived, filed away, and largely forgotten. For decades, they just sat there, until Hamza decided to look at them differently. Here's where things get interesting. Under normal conditions, Earth's temperature behaves in a very predictable way. As you go deeper underground, it gets warmer. That increase follows a steady pattern known as the geothermal gradient. It's like walking into a basement where every step downward feels slightly warmer than the last. But when Hamza and his team started analyzing the Amazon borehole data, they noticed something strange. Some areas were cooler than expected. Others were warmer than they should be, and these anomalies weren't random. They formed patterns wide, consistent patterns stretching across enormous distances beneath the Amazon. So the question became obvious: what could disturb the Earth's natural heat flow on such a massive scale? The answer was water. You see, moving water doesn't just flow, it carries heat. When groundwater moves downward, it can cool surrounding rock. When it flows laterally, it redistributes warmth in subtle but measurable ways. Solid rock alone can't do that. This is where Hamza's decades of experience mattered. Years earlier, he had published research on heat flow gradients in regions like Rio de Janeiro state. He understood how temperature behaves when nothing is moving and how it changes when fluids enter the picture. To interpret what they were seeing, Hamza's team applied mathematical models originally developed in 1965 by John D. Bredehoeft and ISS Papadopoulos. These equations describe how heat and fluids move together through porous media materials like sandstone, where tiny spaces between grains allow water to slowly seep through. This wasn't fast-moving water like a river you can kayak on. This was slow, painfully slow, but over thousands of kilometers and millions of years. Even slow movement leaves a signature, and that signature pointed eastward. Across borehole after borehole, the thermal data suggested a consistent lateral flow of groundwater, moving roughly in the same direction as the Amazon River above, but at depths reaching several kilometers underground. Let that sink in for a moment. No visible channel, no erosion, no surface expression at all. Just heat, quietly whispering that something was moving below. Hamza didn't claim this was a river in the traditional sense. He was careful, scientifically cautious. But the scale of the system was undeniable. When you connect hundreds of wells, spanning an entire basin, and the data keeps telling the same story: movement, direction, consistency, it becomes impossible to ignore. That's how the idea of the Hamza River was born. Not from adventure, but from patience. From looking at old information with fresh eyes. And perhaps that's the most unsettling part of this discovery. If a massive underground water system could remain hidden for decades right beneath one of the most studied regions on Earth, what else might be buried in plain sight? What other secrets are sitting quietly in forgotten datasets, waiting for someone who knows how to listen? And this is only the first layer of the mystery. To really understand how this discovery happened, we need to rewind the clock back to the middle of the 20th century, when Brazil was in the middle of an oil-driven transformation. In 1953, Brazil founded Petrobras, its state-owned oil company. This was a time when oil meant progress, power, and independence. And the Amazon, vast, unexplored, and geologically complex, became one of Petrobras's biggest targets. Throughout the 1960s, 70s, and 80s, drilling rigs spread across the Amazon basin. Wells were drilled deeper and deeper, some reaching nearly 4,000 meters below the surface. Engineers lowered instruments into these boreholes, including thermometers designed to measure subsurface temperatures. Again, the goal wasn't water, it was oil. But science has a funny way of rewarding curiosity long after the original mission ends. Those temperature logs, thousands of measurements across hundreds of wells, quietly became something else entirely: a hydrological time capsule, a detailed record of how heat behaved deep beneath the Amazon over enormous distances. When Hamza began analyzing this data, patterns started to emerge. In the western Amazon, near the Acre Basin and close to the towering Andes Mountains, the thermal profiles told a very specific story. Temperatures dropped more sharply than expected with depth. That kind of cooling doesn't happen by accident. It suggested vertical percolation rainwater from the surface, slowly sinking downward through faults, fractures, and porous sediments. Imagine rain falling on the Andes, then beginning a journey underground, slipping through cracks so slowly that human lifetimes mean nothing to it. As the data moved eastward, something changed. In the central Amazon, within the Solimões and Amazonas basins, the thermal signatures flattened. Instead of vertical movement, the heat patterns pointed to horizontal flow. Water wasn't sinking anymore. It was spreading sideways, guided by pressure differences rather than gravity. And then, farther east still, toward the Maranhão Basin near the Atlantic coast, the data suggested gradual discharge water continuing its silent journey until it eventually met the ocean. All of this from mountains to sea without ever breaking the surface. From these patterns, Hamza and his team began estimating the scale of the system. And this is where the numbers become almost unbelievable. The inferred underground flow stretched roughly 6,000 kilometers in length. Its width ranged from 200 to 400 kilometers. And it flowed at depths between 2 and 4 kilometers underground. At that scale, you're no longer talking about a local aquifer. To calculate how much water might be moving and how fast, Hamza relied on one of the foundational equations of hydrogeology, Darcy's law. First formulated in 1856 by Henry Darcy, the law describes how fluids move through porous materials under pressure gradients. In simple terms, it says flow depends on three things: how permeable the material is, how much area the water can move through, and how steep the pressure difference is. In the Amazon basin, the rock sandstones, shales, and limestones have porosities between 10 and 30%. That means there's space for water to move, but not easily. The permeability is low, extremely low. As a result, the estimated flow speeds are almost shocking. Not meters per second, not meters per hour, but centimeters to meters per year. Hamza's proposal in 2011 was the result of decades of preparation. After moving to Brazil in 1974, he immersed himself in long-term studies of regional heat flow. At a time when global geophysics was rapidly evolving after World War I, oil exploration around the world had unintentionally generated massive datasets, and Hamza knew how to read them. By 2005, he had already published influential work on geothermal gradients in southeastern Brazil. He collaborated with international scientific communities, including researchers connected to organizations like the American Geophysical Union. His expertise wasn't theoretical, it was earned, measurement by measurement. By the late 2000s, advances in computational power finally made it possible to model the Petrobras data at basin-wide scales. What had once been scattered numbers turned into flowing patterns. No textbook diagram, no accepted model waiting to be confirmed. At best, there may have been whispers, ideas exchanged quietly in academic circles, but until 2011, nothing had crystallized. And then suddenly, it did. A river no one had seen, in data no one was looking at, revealed not by exploration, but by interpretation. And that raises a deeply unsettling thought. If something this vast could stay hidden for so long, what else might be flowing beneath our understanding right now, waiting for the right questions to be asked? The moment the idea of the Hamza River entered the public space, the reaction was immediate and intense. Headlines exploded. A hidden river beneath the Amazon. A mysterious underground Amazon, a secret world flowing below the jungle. Some articles made it sound almost mythical, like something pulled straight out of science fiction or ancient legends about subterranean worlds. And honestly, can you blame them? A river thousands of kilometers long, flowing beneath the largest rainforest on Earth? That kind of story grabs people by the imagination instantly. But inside the scientific community, the response was different. Less sensational, more cautious, and far more curious. At conferences and in academic journals, researchers began asking hard questions. Is this really a river or something else entirely? Where does the water come from? How old is it? And how does it interact with the Amazon above? To answer those questions, scientists turned to more advanced tools. One of the most powerful techniques involved isotopic analysis, specifically oxygen-18 and deuterium isotopes. Think of these isotopes like fingerprints. Rainfall from the Andes carries a different isotopic signature than rain falling locally in the Amazon basin. By analyzing these ratios in groundwater samples, scientists could trace whether the water originated high in the mountains or closer to the surface, and the results lean toward a deep, long-distance journey consistent with Hamza's model. Then came data from space. NASA's GRACE satellites, launched in 2002, weren't designed to find underground rivers either. They were built to measure tiny changes in Earth's gravity, which shift as water moves and accumulates underground. Over time, GRACE data revealed something remarkable. The Amazon basin showed increasing groundwater storage, gaining more than 22 cubic kilometers of water per year, at least until severe droughts around 2016 reversed the trend. It didn't prove the Hamza River directly, but it supported the idea that massive subsurface water systems were at work. Now, step back for a moment and notice something important. This discovery didn't belong to one field of science. It required geophysicists to interpret heat flow, hydrologists to model groundwater movement, environmental scientists to understand ecological impacts. Even satellite engineers played a role without ever intending to. That's what made it powerful and complicated. Because with that complexity came uncomfortable questions, especially ethical ones. The data that revealed the Hamza River came from oil exploration in one of the most sensitive ecosystems on Earth. That raised difficult conversations about the relationship between industry and science. Can valuable environmental insights come from extractive activities? And if they do, who gets to decide how that knowledge is used? There was another voice missing at first: indigenous communities. In regions like Acre and Amazonas states, indigenous peoples depend directly on rivers, floodplains, and seasonal water cycles. If surface waters are connected even indirectly to deep underground flows, then discoveries like this aren't just academic. They touch livelihoods, traditions, and survival. That realization led to growing calls for inclusive research science that doesn't just study the land, but listens to the people who live on it. Methodologically, the Hamza River also exposed a deeper challenge. How do you prove something you can't touch? Drilling directly into a system 4 kilometers underground is enormously expensive and technically risky. The pressures, the temperatures, the engineering requirements, it's not something you do lightly. So instead of direct sampling, Hamza relied on proxy evidence. In a way, it's similar to how astronomers detect planets orbiting distant stars. They don't see the planet itself, they see the wobble, the disturbance, the indirect signal that something unseen must be there. Here, heat was the wobble. Thermal anomalies became the clues. To refine those clues, researchers turned to numerical simulations using groundwater modeling software like ModFlow. These simulations allowed scientists to test different scenarios, changing porosity, permeability, pressure gradients, and see which models best matched the observed data. Some debates continue. Is river the right word? How continuous is the flow? How much does it interact with surface systems? Those debates aren't weaknesses, they're signs of healthy science. And when you zoom out even further, the Hamza River starts to look less like an anomaly and more like part of a global pattern. Across the world, scientists have uncovered massive subsurface systems: the Great Artesian Basin in Australia, the Guarani Aquifer beneath South America. But what makes the Hamza unique is its alignment with a major surface river, almost like a shadow twin. A surface river above, a deep, slow-moving counterpart below. Together, they reshape how scientists model entire basins. Vertical flow, in floodplains for example, slow subsurface seepage may help sustain base flows during dry seasons, quietly supporting ecosystems when rainfall disappears. Life persists, not because of what we see, but because of what we don't. And that's the real legacy of the Hamza River. It didn't just reveal a hidden water system, it forced science to look deeper literally and philosophically. Because sometimes the most important systems on Earth aren't the loudest ones, they're the slowest, the oldest. The ones we almost miss entirely. When you step back and look at the full timeline of the Hamza River's discovery, something important becomes clear. This wasn't a sudden breakthrough. It began quietly in the 1970s and 1980s, when Petrobras drilled deep into the Amazon basin, chasing oil. At the time, no one imagined those boreholes would one day help reveal a hidden water system beneath the rainforest. The temperature data was collected, logged, archived, and largely forgotten. Then comes 1974, when Valia Manethil Hamza arrived in Brazil. At that moment, there was no Hamza River, no hypothesis waiting to be proven. There was just a scientist beginning decades of work on geothermal processes, learning how the Earth breathes heat, how rocks store energy, how fluids leave subtle signatures behind. Between 1974 and 2005, Hamza built that expertise piece by piece, publication by publication. Long before anyone talked about underground rivers beneath the Amazon, he was learning how to read the invisible. In the late 2000s, something finally clicked. Computing power had improved. Old Petrobras datasets became usable at a basin-wide scale. Patterns that once looked like noise started to look like movement, flow. And then, in 2011, the idea stepped into the light. At a geophysical conference in Rio de Janeiro, Hamza and Elizabeth Tavares Pimentel presented their findings not as a sensational claim, but as an inference, careful, mathematical, grounded in decades of data. What followed wasn't acceptance, it was scrutiny, as real science always works. Since then, the Hamza River has lived in that space where discovery meets debate. Follow-up studies, new methods, satellite data, isotopes, models refined, challenged, adjusted. No final verdict, no neat ending, and that's the point. This story perfectly captures the iterative nature of science. A preliminary finding doesn't close a chapter, it opens one. Every model begs to be tested again, from a different angle, with better tools. The Hamza River wasn't found in a single moment. It emerged slowly, patiently, across decades, just like the water itself. And with that foundation laid, the history, the data, the methods were finally ready to go deeper. Because now that we know how the Hamza River was discovered, the next question is even bigger. What exactly is this hidden system doing beneath the Amazon, and why does it matter so much? We'll explore that next.